Not all the time.
Gravity.
Okay.
Electromagnetic.
Yeah, we did that on previous, and I got the answer wrong.
Wait, isn't that the wrong word?
No, because it asked me about electromagnetic, and then I was like, I don't know.
Wait, isn't it like gravity, electromagnetic, and strong?
There's really not a secret.
We're not in order, but
In order of like
is never the
weakest to
answer.
strongest.
Well,
Molly,
weak
are
and
you
strong,
on-
but other than that, that's it.
I thought you were.
Okay, so let's talk, Marge, you sum that up. Okay, so on that assignment from yesterday, so on 71, you should have two reactions that happened and two of them that did not. Okay? They might even alternate back and forth between the ones that did and the ones that didn't. But make sure that you have, on each reaction that occurred, okay, you should have four things: the balanced equation, the E naught value, the value of delta G naught, and the value of K. Okay? And writing down random numbers does not quantify that. Okay? Show me what they are. Now, let's talk about how you calculate K, what we talked about yesterday. And this is this big picture on how everything fits together. So, if you look at the value of K, which is 10, the E naught, N over 0.0598. Okay? So here's the whole point of this story, is that the only thing that could possibly be a non-zero value is E naught. Okay? And this is the big picture that I tried to convey yesterday. And this is how it ties in with Ka and how it ties in with KSP. Okay? So if you look at the Ka of a weak acid, like hydrofluoric acid, for example, okay? So hydrofluoric acid is a weak acid. Means it doesn't ionize very much. Okay? Because it has a very strong conjugate base. That fluoride ion really wants to take that back in. So the Ka, if you look at how that's calculated, is that hydronium ion times your fluoride ion concentration divided by HF. Okay? All right? So the only way you can mathematically generate a small Ka value is if your hydronium ion and your fluoride ion concentration are very small relative to the concentration of the acid. Okay? That's the only way it works mathematically. If Ka was a big number, that would mean you had a lot of hydronium ions and a lot of fluoride ions and very little of the original form of the acid. So Ka values are small mathematically because you don't produce very many hydronium ions and very many fluoride ions. Because the fluoride ion is the conjugate base off of a weak acid, so it really wants to take that proton in. Now, mathematically, how you generate a small K value is that you have a negative E naught value. So this is where this goes full circle. So if you have a negative E naught value, what do you know about the spontaneity of the reaction?
Spontaneous.
It's non-spontaneous. Okay? So a negative E naught value is non-spontaneous. So when you take 10 and you raise it to a negative exponent, you get a small number. Okay? So that's where that kind of goes hand in hand. You look at KSP. So for example, on number 75, you were to find the KSP of cadmium sulfide. Okay? So let's just think this through. You have two redox reactions there, right? Excuse me, you have two reduction reactions. They're both reductions. So you want to determine the KSP for this based upon these standard potentials. So think this through. This is, again, don't get wrapped up in the math. See the big picture. When you calculate that KSP value, this is why we cited KSP before we did this. Are KSP values notoriously big or notoriously small values? Isaac. They're very small numbers, okay? So when you calculate KSP, and there's two ways you can calculate KSP. In this situation, you're talking about cadmium sulfide. So one option, how you can get that, is to go, okay, that's my cadmium ion concentration. That's my sulfide ion concentration. Okay? That's one way you can get the KSP value. Okay, it's valid. You know, the cadmium and the sulfide concentration are in a 1-to-1 ratio. You can get the KSP value that way. Because this works, because cadmium sulfide is trying to turn into cadmium ions and sulfide ions. So let's say you need to rearrange those equations on number 75. Okay? So there's two ways you can figure out what you have to flip. And you need to understand both of them. One of them is that you need to cancel out the electrons. So you either flip the cadmium sulfide, the one on top, or you flip the one on the bottom. Those are your only two. One of those has to get flipped. Okay? This is basically reduction oxidation reaction. So here's the story. So why are you not going to flip that top reaction that says CDS plus 2 electrons turns into cadmium plus S2 minus? Why aren't you going to flip that one? There's two reasons why. What do you have to express the reaction for the dissolution of cadmium sulfide? What do you have to have as the reactant? You have to have cadmium sulfide as a reactant. That's the whole point. If you flip the first one, you put cadmium sulfide as a product. Okay? Okay? So that's not reason number one. Oh, I have to start with cadmium sulfide so I can't flip the first one. The other reason that you can't is because if you flip the top one, then you have positive 1.21 volts, and you'd have a negative 0.402 volts, and then you'd have a positive E naught value, which when you plug it into the calculation of K with a base 10, you'd get a really, really big value. So there's two reasons why you flip the bottom one. Number one, it allows you to cancel everything out so that you end up with the equation to describe the dissolution of cadmium sulfide. And the second reason is that allows you to end up with a negative E naught value. So on 75, that value of your KSP should be something times 10 to the negative 28th, which is a really, 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 really small number. So what that means is if you put cadmium sulfide in water, the concentration of your cadmium ions and the concentration of your sulfide ions are going to be really, 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 really small. Like 10 to the negative 14 small. Okay?
Yeah, you flipped the wrong one.
You got something to the what?
Positive 27.
You flipped the other equation.
No, he just talked about that. We open our ears? I mean, no, we didn't. Yeah, we didn't. He just talked about it.
Okay, let's talk about 83. Okay? So on 83, and this is where you're trying to figure out molar mass and you're trying to figure out the identities and stuff. So you have a molten metal chloride. So it's some metal Cl3. So let's just kind of think of the bigger picture there. In what group of elements could M not belong to? Couldn't be in group 1. Why? They're all group 1. They all have 1. Okay, if it was a group 1 element, it would be something in Cl. Can't be group 1. What about group 2? Can't be in group 2 either, because group 2 would be something Cl2, because they have 2 valence electrons. So what that tells me is this element, whatever it is, has to be in the middle, maybe to the right of on the periodic table. Okay? It cannot be group 1 and it cannot be group 2. Now, when you get to 78, or 83, excuse me, you want to know what's the identity of the metal. Now, remember, molar mass. This is important. Technically, molar mass means, like, for example, carbon. The molar mass of carbon is technically 12 grams per mole. So the technical expression for molar mass is grams per mole. So what you know is that you run this thing for a certain amount of time, and it deposits 1.41 grams of the metal. So the top is going to be 1.41 grams. What you have to figure out is how many moles that is. And then you're going to take that mass of 1.41 and divide that by the moles. So you need to do stoich. Start with, on that one, you need to start with the seconds. You know the current. You know Faraday's constant. Now, here's what's implied, and this is what you kind of have to think through a little bit. You know that this thing has a charge of 3 plus, because it's MCl3. Okay? So what that means is that this metal is 3 plus 3 electrons, making the metal. So what that means is that now you know this ratio between the moles of the element and the moles of the electron. So if you do 83 right, what you're going to do is you're going to find the molar mass, which should be in the 40s, and then you're going to go to the periodic table and figure out which element matches that molar mass. Okay? So your identity on 83 should start with the letter S. And it's not sodium. It's a metal. Skippy.
That was Will. What else do we got here?
Okay. 95 and 96 are just basically big massive stoich problems. Your answer to 96A should be 200-ish grams. And your answer to 96B in minutes should be around 1,000. Anything else? Are you all good? Okay. So, staple the work to the back of the sheet. That way it's all together. Make sure your names are on it. Olivia Pruitt.
It is. Oh, wait.
Make sure Nathan doesn't burn it off.
Yeah, Nathan.
And make sure Jordan doesn't staple it.
No, that was Natalie.
Oh, it's Natalie. Natalie. All right, so get that handed in. So stop, you on the camera, please.